Welcome back, everyone. So we're getting closer to the end of this lecture cycle. So let's just get back into where we left off last time. We were still talking about in CCA secure public key encryption. And we saw the construction of RSA key encapsulation mechanisms, right? Where we essentially just do textbook RSA, but we're encrypting a random message R with textbook RSA, and what we use as key afterwards that we output from this chem is let's see, where is it? Yeah, here it is. The key is just the hash of this random message under a random oracle, right? And we went into the security proof, which of course uses random oracle magic. We've written down the InCCA experiment for our key encapsulation mechanism. Just replacing the generic algorithms with the keygen encaps and decaps algorithms for the RSA chem. And we want to sort of reduce the security of this to the RSA assumption, right? In the RSA assumption, we're being given something like this, an N, an E, and a C star. And we are looking for an R such that C star to the, such that R to the E equals C star modulo N. That's the RSA assumption. So how do we do this? Well, we noted that the issue was that in order to simulate the decryption oracle in the way it is written here, we need this D, right? We require this D, but if we ourselves are a reduction who just receives N, E, and C star, we don't know what D is, right? We don't have the secret key, so we need to find an alternative way to simulate this decryption oracle. And the idea is, in fact, to use the power of the random oracle, right? The basic idea is that the C's that are being sent here, right? Either they are exponentiations of some R which were queried here. These C's of the form R to the E, which we can efficiently test. Then we know what we need to answer, right? Because then we just know that, well, instead of computing R as C to the D, then we just take R from a list that we're keeping, right? So we're simulating the random oracle by keeping lists of all the queries. On the other hand, if he queries a C here, which has never, which doesn't stand in this relation to an R that has been queried before, then we can just make up something, right? Then instead of trying to decrypt our C and then setting K as H of R, we just come up with something for our K, because he will not be able to test. The adversary will not be able to test this anyway. So let's maybe write this down. So we have this here. So we have our A prime, or this is, let's write this differently. Let's say this is the RSA adversary Adversary A prime. What does it do? Well, internally, of course, it simulates this experiment. And what it does is, well, it just chooses a key, let's call it K hat. Is it, oops, I call it K hat. Yes, K hat, we just choose uniformly at random. And what we do is initialize two lists. The first one, the first one we call list H. This will record all the queries to the random oracle H of queries responses to H, right? This consists of pairs RI-KI, right? So each RI which is queried, which will be queried to the random oracle H, will be stored in that list together with the response, right? Since we're having a random oracle, this Ki is just uniformly random the first time such a query Ri is asked. So in order to simulate this random oracle consistently, we have to at least store these Ki. We have to store these Ki. And the second one, the second list, we call LD of queries responses to the DEC oracle, right? The DEC oracle. Cool. And this consists of pairs CI, KI. And now we have the following simulation strategy, right? So our adversary A might want to query H. Let's make this kind of like this. He queries H with an RI, and how we're going to simulate this is first we check if this if RI-KI for some KI is element in LH, right? If essentially we're checking if this RI has been queried to H before. If so, output KI, right? That's easy. We just have to answer consistently. If the adversary queries the random oracle several times with RI, we have to provide the same answers. Otherwise, we check if RI to the E mod n, of course, mod n, comma KI is in this list LD. So what we're checking is for this RI that he sends to us, whether he already submitted a similar or a related query right? Here we have CI and back go KI to the decryption oracle, right? We'll provide him with this random oracle, this random oracle and this decryption oracle. And whenever he sends us this such an RI to the random oracle, first we check if RI has been queried to the random oracle before. Next, we check if a related query, right, namely RI to the E mod N has been sent to the decryption oracle. And if so, we also have to answer consistently, namely output KI. Now, otherwise, of course, the third case, we just choose KI uniformly random, right? This means this RI has not been queried before. Store RI, comma KI in LH and output KI. So there's one more thing. We don't just, our adversary A prime doesn't just have to simulate these oracles. It also has to break the RSA's A challenge. There's sort of the final case here. If it holds RI to the E mod N equals C star, right? Where the challenge that our adversary gets will be N comma E comma C star. That means the adversary A reveals with this query RI a solution to this RSA inversion problem that we're trying to break. Okay. Then abort simulation and output RI. Okay, that's for the way we simulate the random oracle, right? And the idea is, of course, since the random oracle behaves randomly, the only way for our adversary A to win this experiment here, I'm not going to show this in detail, but is to query such an RI such that RI to the E equals C star. Otherwise, the adversary wouldn't be able to distinguish whether the key K hat is a hash of the RI, or which is the correct decryption of C star, or was just chosen uniformly at random, right? And the second thing that we have to do is, of course, simulate the decryption oracle, but we're also going to do that with these two lists. So if there is a CI, comma KI element LD, output KI, first check, right? Second check. Otherwise, if there is a pair RI KI in LH with RI to the E mod N equals C, output KI. And of course, there's always a possibility that this CI is unrelated to all the queries that has been asked before. Otherwise, choose KI uniformly random in 0, 1 to the lambda, store ci, comma ki in LD, and output ki. So really the magic of this reduction of this adversary A prime is to simulate these two oracles, the random oracle H and the decryption oracle DEC jointly, right? That's the whole magic. Instead of how it's in the real experiment, simulating them individually, right? He's sort of keeping a joint state, this list LH and this list LD, to sort of come up with a convincing story for the adversary A. So we can show sort of this is follows rather routinely that the simulation of this adversary A prime and the INCCA experiment for the chem are in fact identically distributed. So in order for so the second thing we can show that if this adversary A here wins or wins the INCCA experiment with non-negligible probability, then it must send such a red query here. Then he must at some point send a query Ri to the random oracle. Otherwise, his advantage is 0. So good. Someone is asking on the chat, can you explain the second otherwise in DEC? Should this not be output Ri? No, we always output keys. So both the random oracle and the decryption oracle output keys. So that's actually a very good question. So the decryption oracle here, right? Let's look into this. You're bringing up some very good point. Let's maybe just jump to the corresponding slide. Look at this. The decryption oracle for chems does not just invert the RSA function for our case, but always outputs a key, right? That's sort of part of the magic why all this works. We can go back here, right? If you look at this decryption oracle, the decryption oracle outputs the key, not the R. Good point. Okay. And this output Ri, right? This means this is not the output here. This Ri does not go back to the adversary A, but this is the actual output of A prime. Okay, good. So now we spent some 20 minutes on this. Let's quickly do the summary of the chosen ciphertext attacks. So chosen ciphertext attacks, as we have seen, are an even bigger issue in the public key setting than in the private key setting, right? We've seen Bleichenbacher's attack, which, given just a ciphertext validity oracle, which is oftentimes really hard to avoid when you have distributed protocols where you might have transmission faults, you will get something you will get some kind of you need some way to show ciphertext validity. So someone is asking on the chat, how is a scheme called? We just proved the security again. This is just typically known as the RSA key encapsulation mechanism. I think that this is also how we called it, right? I mean, I could go back here, but yeah, RSA-based key encapsulation mechanism. I mean, this is typically known as the RSA chem. Good. So Bleichenbacher really made an important point by showing that even a little bit of sort of correctness information about ciphertexts can fatally break a otherwise fine encryption scheme, right? People hadn't put too much thought about the CCA security of PKCS1 is up until that point chosen ciphertext security was more of a theory thing, right? Theory people thought about this, but practitioners was like, yeah, we've never really seen an issue here, and this all changed with Bleichenbacher's attack. Okay, so CCA attacks became a very real practical concern. So there's a comment on the chat, but the design of PKCS was also very unfortunate. I mean, hindsight is 2020, right? Maybe another design would have had a different shortcoming if there was not sort of a rigorous security analysis in the form of a security reduction, right? Okay. So we've defined chosen ciphertext security for both public key encryption and key encapsulation mechanisms, essentially analogously to the private key setting. And we've seen that in CCA secure public key encryption, we've seen this without a proof, can be obtained from an in CCA secure CAM and in CCA secure private key encryption. And of course, the new ingredient here that we still had to provide was the in CCA secure CAM. And this is what we've just seen from the RSA assumption, right? We can do this from the RSA assumption. Now, of course, the story doesn't stop here, right? Cryptographers, in particular, cryptographers in the let's say in the gray area between theory and practice, they love constructing in CCA secure encryption schemes from all sorts of assumptions. And by now, essentially, I mean, it is safe to say that essentially all concrete assumption, all or from every assumption from which we know CPA secure encryption, we also know CCA secure encryption. On the other hand, generically, if you just give me any CPA secure public key encryption scheme, we don't know how to turn this into a CCA secure public key encryption scheme without the help of random oracles. If we're allowed to use random oracles, we know how to do this. If not, this is still a great open problem in theoretical cryptography. Build CCA secure encryption. Maybe for those who are interested, let me just note that. So CCA PKE from any CPA PKE with random oracle, right? Maybe write that out. Random oracle. We have the so-called Fujisaki Okamoto transform. Fujisaki Okamoto transform. And without random oracle, this is an open problem. One of the great open problems right now, where in the last few years there have been some advances, right? So there has been a little bit of progress in this area. So we don't yet know how to do it for any CPA secure PKE, but if you give me a CPA secure PKE with a little extra property, something called witness recovering, which means that decryption also outputs the random coins that were used to encrypt, then we in fact know how to do this. Good. Okay, so much I see a question in the chat. Open problem for theory, or would this have a great benefit? Look, I mean, this is a scientific problem, right? First and foremost. I mean, now I wouldn't see any immediate practical repercussions, because essentially all the schemes that are used in practice at some point use hash functions in a way that is modeled as a random oracle in the proof, right? It seems practitioners are very comfortable with the random oracle heuristic, but I mean, this is first and foremost a scientific problem, right? This is the scientific question of what is really necessary to construct CCA secure PKE. I mean, you might call this maybe a little bit spleeny, but I mean, this is the same. Theorists go after this for the same reason that physicists try to find, for instance, particle physicists try to find a successor to the standard model of particle physics, which they know is incomplete, right? This is a first and foremost scientific question that doesn't yet have immediate practical repercussions. But good, so much for that. Let's move on. Namely, to digital signatures. All right. Good. So we've seen symmetric key encryption, message authentication codes, public key encryption, and now we're moving into the last quadrant, digital signatures, which are, I mean, as this diagram says, a public key primitive to ensure authenticity of messages. Let's quickly recap authentication for this, for this purpose. So we know that message authentication in message authentication code, every sender and receiver has the same key K. So what this allows us is to ensure integrity of messages within a closed group, right? We have a group of people who all have the same key. For instance, Bob can send a message to Alice and provide a MAC here. But of course, here authentication is in some sense symmetric. Anyone who can verify authenticated messages can also produce authenticated messages, right? The key K is dual purpose. It's being used to authenticate and to verify. So this, of course, reminds us of the setting how we had it for encryption. In private key encryption, the key is used both for encryption and for decryption. But then in public key crypto, we all of a sudden had different keys for encryption and decryption: a public key for encryption and a secret key for decryption, right? And now you might ask, once you have such an authentication code, whoops, if you authenticate yourself to your bank, then the bank, using an authentication code, then the bank necessarily has the same key K as you. So that means if you send a transaction to the bank, and authenticate it with a message authentication code, then the bank needs the same key. So if you were to use message authentication codes, you would have to trust the bank really very far not to not to abuse this key K. Now, of course, this is fine with a real bank, let's say with an actual bank who has something to lose, but think of trying to do something, say, on a blockchain, where you don't actually have a physical bank, but what's actually the bank in the real world is just a giant public ledger. So yeah, someone wrote on the chat, I mean, you entrust them with your money already. That's true with an actual bank. This is like you give them your money and they can do anything with it. What we'd like to do is put some more cryptographic constraint on such a bank, such that you need to put less trust into your bank. So right now, with an actual bank, you need to give them a lot of trust. But whenever we pour crypto sauce on such an application such as banking, right, we want to reduce trust, right? We always the final purpose of crypto in almost all applications is to reduce trust assumptions. You can typically in all kinds of applications you still have some trust assumptions. You need to trust in something minimal, but what we're using crypto for is to reduce the amount of trust, and that's sort of what now brings us to digital signatures, right? Can we separate the tasks of authentication and verification such that this again becomes an asymmetric process, such that, for instance, your bank, and again, think of not your physical bank, but maybe something in the internet like a blockchain, will be able to verify your transactions, but will not be able to make new transactions on your behalf, right? Which would be possible using message authentication codes. And now let's again jump back in time. This leads us back to the year 1978. And in fact, this is sort of, as far as I remember, sort of the main reason why Rivest, Shamir, and Edelman got the Turing Award for their work, because they basically took crypto to the next level. So up until RSA, crypto was all about encryption and let's say symmetric authentication. But RSA were the first to introduce this new concept of digital signatures. So what are digital signatures in a nutshell? To authenticate, or now we call it signing, we use a secret signing key, whereas verification of a signature is done using a public verification key. And in that sense, this was the first non-encryption use of cryptography, right? Right until that point, all of cryptography was essentially about encrypting stuff. So yes, authentication did exist already, but it was not, up until that point, was not considered through a cryptographic lens, right? This whole stuff that we did about message authentication codes and or whatnot, this, at least on a foundational level, happened only after RSA. Good. And really the idea of Rivest, Shamir, and Edelman to produce or to construct a signature scheme was super simple, right? We've seen in RSA, encryption and decryption are almost the same thing. To encrypt in textbook RSA, you compute this R to the E, and to decrypt, you compute C to the D, both modulo N. And the idea of Rivest, Shamir, and Edelman, how to turn this into a signature scheme, was just to reverse roles, right? Instead of first encrypting and then decrypting, they said, oh well, let's take a message, let's say M, and just decrypt it first, right? There's nothing that stops you from this, computing M to the D mod N using the secret key D. Now, anyone who has the public key N comma E can now, let's call this thing, signature, let's call this sigma, right? We can attach the signature to such a document. Anyone with the public key PK, which consists of N and E, can now just compute sigma to the E mod N and test whether this is, again, the same as M, right? We know from the correctness of RSA that M to the D times E is congruent M modulo N. Okay, so because D times E is congruent 1 modulo phi of N. Good. And now we've seen that this RSA signature scheme has the correct functionality, but what about security? The idea, and this idea is slightly flawed. It's not terminally flawed, but it's slightly flawed, is that this RSA function, M to the E mod N is hard to invert, right? Essentially computing M to the D without knowing phi of N or without knowing D is hard to compute. So it shouldn't be possible to sign without knowledge of the secret key. That was their idea, right? If you have, let's say, a document M and you want to sign it, you would have to find a pre-image of this document under the RSA function, and this should be hard. Now, you're already seeing this, we're not using any randomness here, so there's probably some issues. So what's the first issue one of you could think of? With this simple RSA signature scheme? Replay attacks. Replay attacks are in some sense always possible, right? If I give you a signature on some document M, then this signature is in the world. There's no way to recall it. There are signature schemes which allow for that, but not that's a very advanced topic. So replay attacks, once a message has been signed, the signature is out in the world. That's sort of the same issue as we had for authentication. Typically, you're not just signing a message M, but a timestamp message M. Okay, let's look maybe for a little bit more cryptographic issues that could come up with this scheme. For instance, if I was to ask you what's a meaningful message, right? Shrug, right? It's we know it's typically hard to formalize what constitutes a meaningful message. So typically we just say, well, signing in this case shouldn't be possible for any new message for which you haven't seen a signature for. Okay. Someone wrote on a chat, what's a meaningful message? A message you can draw information from. That's really, really hard to formalize. But good. Let's go into the first issue. namely textbook RSA is malleable. So someone asks, what if two messages are congruent? I mean, that essentially means the way we've just defined the RSA signature scheme. When they're congruent, they are the same. When they're congruent, modulo n, they're the same. But okay, let's go into an actual attack. Exactly. Someone wrote it. Probably this is something related to the homomorphic property of RSA, and that's in fact true. So let's say we are given signatures on messages M1 and M2. Then, since textbook RSA is homomorphic, we can create a signature on M1 times M2. Right, good. Let's maybe write this here. So if you have sigma 1 as M1 to the D, right, and sigma 2 as M2 to the D, then of course, using those two things, you can compute sigma 1 times sigma 2, and that's M1 times M2 to the D, right? And of course, now, which is now, of course, equivalent to sigma 1 times sigma 2 to the E equals M1 times M2. So now you are able to produce signatures for messages that are the product of messages for which you have seen signatures. This should not be, ideally not be possible, right? Because you could do that without knowledge of the signing key, right? You could all of a sudden produce a fresh signature without being in possession of the signing key. That's not something that we want. But there's yet another issue, right? For instance, just choose yourself an R, right? And then set sigma to R to the E, right? Sorry, no, the other way. Now I messed it up. Choose yourself a random sigma and set the message M to be sigma to the E, right? Of course, if you choose sigma random or in whatever way, then M will also be random, right? But what this allows you is to produce pairs of message and signature without knowing the signing key. Okay, and the issue is textbook RSA allows you to choose first the signature and then the message depending on this signature, right? This will be a weird message, but anyway, the message or the signature will verify for the message, right? And sometimes there are really protocols where you just sign random messages. This happens often enough that to prove your identity, someone sends you a random message and you return a signature of this random message. And clearly the textbook RSA signature scheme would be insecure in this setting. So question is, how should we define security for signatures? And of course, we take inspiration from the world of private key cryptography. And here's an important thing, right, which I cannot overstress. RSA made it look like signatures are the reverse of public key encryption. So just take a public key encryption scheme, run it in reverse, and you get signatures. This works sort of, right? We've seen this approach has issues. This works sort of for RSA, but in general, this doesn't work. So I could even go way further here and say so that's maybe a big spoiler. Digital signatures can be constructed from any private key encryption scheme, right? That comes sort of as a surprise that for signatures, even though it seems to be something public key, you can build it from any private key encryption scheme. Whereas, as I've said before, for public key encryption, this is a grand open problem, constructing a public key encryption scheme from any private key encryption scheme. Good. So this is really a fallacy that I cannot overstress, that even though RSA made it look like at first glance that signatures are the reverse of public key encryption, this analogy doesn't really carry far. Good, but someone's asked a question. Why was textbook RSA malleable again? Well, exactly because of this fact here, right? If you give me M1 to the D and M2 to the D, if you multiply those two together, it gives you M1 times M2 to the D, right? That's just simple algebra. Okay, good. So let's do what we always do and first define what a signature scheme is, right? Before we can really critically assess security of signature schemes, we first have to define what a signature scheme is. And a digital signature scheme consists of 3 PPT algorithms: gen, sign, and verify. Gen is a randomized algorithm which takes as input, as always, the security parameter and outputs a pair of verification and signing keys. Now, we call the public key not PK anymore, but VK, just to disambiguate this from public key encryption. So typically for signatures, we call the public verification key VK instead of PK. The sign algorithm takes the signing key and a message M and produces a signature sigma. The verify algorithm takes as input the verification key VK, a message M, and a signature sigma, and just outputs a single bit, B in 0 and 1, which of course tells you if sigma is a valid signature for the message M. And already here you can tell that this analogy that signatures are the converse of public key encryption doesn't really carry far, right? Because encryption takes a message and outputs a ciphertext, and decryption takes a ciphertext and outputs a message. But now here, verify just outputs a bit, right? So how could you, for instance, turn such a verify algorithm into an encryption algorithm? That's already problematic on a syntactic level, right? Because verify does not take a signature and output a message. It takes both a message and a signature and tells you if the signature is valid for the message, right? So already on this syntactical level, signature schemes are different from public key encryption. And of course, the first property we have to look into, we look into is correctness. So someone is asking on the chat, if SK equals VK, we have essentially a MAC. I mean, I would write it if VK contains the SK, then yes, this is a MAC. If you put both keys together, this is both in terms of functionality and in terms of security a MAC. So in terms of correctness, we ask that if you give me any message M, sign it, and then verify it with the corresponding verification key, then this should always output 1. Where, of course, VK and SK are correctly formed pair of verification and signing key. Okay, that's for correctness, essentially the same as for max, except that now verify uses the verification key instead of just the secret key. Good. And we've seen the security definition for message authentication codes. Now, the natural thing to do is to adapt this to the setting of signatures. With, of course, now we'll have a small twist. We recall that for message authentication codes, we had to give the adversary a authentication oracle where he can send pairs of message and authentication tags to, and the oracle would tell him if they are valid or not. Whereas here we also had an oracle which produces authentication tags, but here we proceed as follows. Okay, good. This is bad. This should be VK and this should just be Gen. So the challenger generates a pair of keys, VK and SK. And now the adversary A gets access to a signing oracle, which he can query with messages MI and get signatures sigma I. Okay, that are signed using the signing key SK. And of course, now he can verify these signatures using the verification key VK. And what's his goal? In the end, he has to produce a message M star and sigma star, such that on the one hand side, sigma star is a valid signature of M star, right? But on the other hand, M star was never queried to the signing oracle. Let's maybe write that out. M star was never queried to the signing oracle. And if sigma star is a valid signature of M star, we output 1, otherwise 0, and we call the output of this experiment EUF CMA. And as usual, we say signature scheme Gen sign verify is EUF CMA secure if it holds for every PPT adversary A that we have a negligible function nu such that the winning probability of A is in this experiment is bounded by nu. All right, so this is the definition of or the standard security definition of digital signatures. There are slightly stronger versions of this, right? In the private key setting or in the message authentication code setting, we have seen strong EUF CMA security where the adversary might actually output an M star, which it has queried to the signing oracle before, as long as it produces a new signature sigma star. And we can do absolutely the same thing here for message for digital signatures, right? We can strengthen the security definition and also do various flavors of the security definition, but that's sort of the, let's say, the base security definition is EUF CMA security for message authentication codes. Yeah, digital signatures, sorry. Good. All right, so let's quickly look at some applications. How can we, how are digital signatures actually used? Why are they so important in the internet? So how can you, question is, how can you trust a web service, right? Let's say someone runs a website and says, let's say, pretends to be Amazon, right? How can you trust that you're really speaking to Amazon? So let's say this site has a public key, and you would like to trust that this is actually the public key of Amazon. So if you encrypt your messages under this public key, only Amazon will be able to decrypt them and not some other imposter. Okay, so the way this is currently implemented in the infrastructure of the internet is via so-called certification authorities. And a certification authority is essentially a service that you need to put some trust in, right? You need to trust the certification authority. And if you trust them, they will certify that, let's say, some web service is actually to be trusted. So what that allows us to do is to reduce trust. Now, now instead of having to trust every single website or every single web provider, you just have to trust the certification authority. Here's the thing. So the certification authorities are probably provided by the internet providers. No, they're not provided by let's say the German Telekom or Vodafone. They're sort of international organization, right? They're in some sense these certification bodies are in some sense NGOs, sort of yeah, how, I don't know how to best describe that, but they're typically not run by profit-oriented businesses, right? This is these certification authorities are, or who have the who issue these root certificates are typically how to best put this, international organizations, right? We can look that up on Google and Wikipedia. Okay, but how does this actually how does this actually work? So you have your certification authority, and what they do is, let's take our internet provider, for instance, Amazon, and Amazon can go to this certification authority and ask for their keys to be signed, right? There's the certification authority now signs the keys of Amazon, and that will allow you, who, let's say, has the verification key of this certification authority, right, to trust the key of, let's say, Amazon, right? You trust things that were authenticated or signed by the certification authority. And if someone comes with a public key that has a certificate, a signature from the certification authority, you, or better, your browser, will trust it. Right? Someone wrote in the chat that the root certificates are actually typically hardwired in your browser. And the nice thing about certification authorities is that this trust in certification authorities can be bootstrapped in some sense. So you have this, for an example, the X509 standard, where you have a verification key for root certificates. And these certificates first certify that some, let's say, an email, the verification key of an email certification authority is to be trusted, or a TLS certification authority, or a software certification authority. So in essence, what you get here, right, are signatures on VKs of lower tier authorities. Okay, I can basically certify that an entire organization is trustworthy by signing their verification key. And now the great thing is now you can actually chain these signatures. Okay, someone asks, sounds a lot like a single point of failure. You're absolutely correct. The signing key of the root certification authority, I mean, that needs to be really, really, really well guarded. If you can produce signatures for the root certification authority, then you can basically inject malicious software into arbitrary devices, right? Whenever your computer gets a software update, of course, these updates need to be signed by the software certification authority. And now, if a hacker gets access to, say, the root signing keys, then shit hits the fan. Absolutely, this is a single point of failure, and yeah, these things need to be super well guarded. Okay, good. Okay, but now that we've talked about how to actually use signatures, well, to authenticate the authenticity of web services, software services, software updates and whatnot, let's actually look into how to construct signature schemes. So, as I've mentioned before, the idea how to build signatures was introduced by Rivest, Shamir, and Edelman, who said, in order to produce who basically said, here, reverse textbook RSA, doesn't that look like a good signature scheme? We've seen this has issues because of the homomorphic properties of RSA, but as we've seen with key encapsulation mechanisms, that the textbook RSA encryption scheme can be turned into a good key encapsulation mechanism by just encrypting random messages and deriving keys from these random messages by hashing them. We can do sort of kind of the same thing in reverse for RSA signatures. And this leads us to RSA hash and sign. And in fact, this will be an EUF CMA secure variant of the RSA signature scheme. The idea here is that instead of just taking a message M and raising it to the power D, we first hash the message. It's really the most basic thing sort of you could do or you would try to do if you have seen how we do this for message authentication codes, right? For message authentication codes, it's of course also the natural thing to first hash the message and only sign the hash value. So what we do here is, given a message M, we first hash it and compute a signature sigma m by just raising this h of m to the power d modulo n, of course. So let's say we again have our RSA instance generation algorithm and a hash function which maps to Zn, which takes any message and outputs an element in your RSA ring. So the RSA hash and sign scheme is given as follows. So to generate a pair of verification and signing keys, we just run RSA gen. Verification key is NE, signing key is ND. To sign, as I just wrote it, we first compute h of m and then raise it to the power d. So instead of raising m itself to the power d, we first hash it. And to verify a signature on a message m, we first hash the message m and then check if sigma to the e is the same as h of m. If so, we output 1, otherwise 0. And interestingly, so here, this is of course not the same as the RSA key encapsulation mechanism. So in RSA key encapsulation mechanism, we were hashing the output, right? There sort of a raw key R came out and we were hashing this raw key. Whereas here we're hashing the input. A message M comes in and we first hash the message M before computing the signature, right? So here hash the input, in key encapsulation mechanisms, hash the output. But both seems to work because we're getting this theorem here, which says that let's assume that the RSA assumption holds, and let's further assume again that H is modeled as a random oracle. Then the RSA hash and sign scheme is in fact EUF CMA secure. And let's quickly see the main idea why this is the case. And for that, let's, of course, first write the EUF CMA experiment for RSA hash and sign. As always, on the left side, we have our adversary. And here we have our challenger. And of course, the challenger runs the RSA gen algorithm. And what we're going to send the adversary is, of course, the VK, which consists of n, e. Now, the adversary wants access to a signing oracle. Let's maybe push that a little bit to the side. The signing oracle, which he queries with messages MJ. And the signing oracle, right, first computes a hash value HJ as hash of MJ and computes a signature sigma J as HJ to the D modulo N. Okay, so then sigma J goes back. This is what our signing oracle does. And of course, we're in the random oracle model. That means the adversary doesn't just get access to the signing oracle, but also to the random oracle, right? So he can send messages, let's call them MI. I mean, here I'm going to call them MI prime, and he gets back hash values HI prime. to the random oracle. In the end, he outputs m star, comma, sigma star. And when if m star is of course not in m1 to m, let's call it mq, right? Where m1 to mq are the signing queries, and of course sigma star to the e modulo n equals h of m star. Good. So this is what our challenger does here. Let's clean that up a little. Where, of course, our let's say M1 to MQ are queries to the sign oracle. And since we have a second oracle, the random oracle, we also give these queries a name. M1 prime to M prime Q prime are queries to the random oracle. Queries to H. Okay, now before we proceed, let's maybe wait for a moment, or let's maybe think for a moment and see how could we use such an adversary to break the RSA assumption. So someone asked a question, the element sign is inverted. Oh, thank you, of course. If M, not in M1 to MQ, thank you. Good. Okay. Yes, this is our EU FCMA security experiment for RSA hash and sign. Let's assume, again, someone from the outside gave us some n, comma, e, and let's call it c, right? Let's call it maybe again c star as before, an RSA challenge. So we're tasked with finding an R such that R to the E equals C star modulo N. How could we do this? How could we go about this? We need to make a few observations first. So someone writes in the chat, again, we don't have D, so we need to simulate the signing oracle according to previous queries. This is correct. The first challenge is the signing oracle. But then the second challenge will be how do we actually get an ETH root of C? So how do we turn whatever the adversary does into, let's say, a value H such that, right, somehow we need to, let me use orange, we need to get to some H such that H to the E mod N equals C star. How do we get such an H from the adversary? What can we do with him to sort of tickle out such an H from the adversary? Where, okay, or maybe phrased differently, where can we actually inject him the C star, right? So the reduction has its own challenge C star, where can we give this to the adversary? Where can we pass this on to the adversary to in fact compute an h such that h to the e equals C star? Aha! Someone wrote something on the chat as a hash of some m. This is correct, but why is that correct? What can we let's say about this? Let's make it in orange, m star. So in order to develop this thought, this correct thought that you've written here, let me maybe ask the following thing. What happens if the adversary A has never queried H to the, M star to the random oracle H? What happens then? What can we sort of routinely conclude if M star was never queried to H? What's the probability that anything, any signature sigma star that he sends will verify for a message M that has never been queried before to the random oracle? Correct. Someone writes, the attacker's advantage is negligible then. And why is that the case? Well, if M star, make a line here, was not queried to H, then H of M star is uniformly random, right? From the view of the adversary. So it holds for whatever sigma star is, for any sigma star, we have then sigma star to the E mod n, or the probability that sigma star to E mod n equals H of M star is negligible, right? So an adversary who does not, that's the important observation here, an adversary who does not query the forge message M star to the random oracle will automatically have only negligible success probability. So we know that if an adversary has non-negligible advantage in forging a signature, then he must tell us what this M star is beforehand, right? Before he outputs it with the in his last message, he must have queried M star to the random oracle H. So now there's Q prime queries to the random oracle H. Where should we should we embed the C star? How should we so we have to embed our RSA challenge at one point. Where should we do this? By the way, this should not be H here. Sorry, this should be a sigma. Why did I write an H there? So there's Q prime messages. Which one do I choose? The first one, the last one? Any guesses? I know that one of these messages, mi prime, will be eventually used as the forge message m star. But I don't know that ahead of time. What can I do? Someone says the first one. So if you take the first one, I'm gonna give, I'm gonna build an adversary who always uses the second one. So going for the first one is probably not a good strategy. All right. Someone writes a random one, and it's exactly what we're doing. The adversary doesn't know if we choose a random one, the adversary doesn't know where we actually embed our challenge, and that's in fact how we do it. So our reduction now works as follows. Again, we have our RSA adversary A prime, which does the following. So the very first thing it does is he just chooses an index I star randomly from 1 to Q prime. This will be the hash query in which we're gonna embed our own challenge, right? So the RSA adversary gets as input n comma let's say n comma e comma c. Let's just call it c here. And now we're gonna do the following. So again, we have our adversary A, and we need to play this game with him. So the first thing, of course, is we need to give him the verification key, which is n comma e. That's fine. That's what the RSA adversary A prime directly gets from his own input, n comma e comma c. So now we need to simulate a decryption, a signing oracle to him. He queries these mj, and we do kind of the last thing as last time. For every new, right, mj, that's mj that he hasn't queried before, we just choose sigma q from Zn uniformly random. This is something we can do. We said age j to be sigma j to the e mod n, and program h of mj to this little age j, right? So the idea, what we're doing here is we're first choosing the signature, and then we're choosing the hash value depending on the signature. We're allowed to do that because we're in the random oracle model. Yeah, that's a cheat, but proofs in the random oracle model typically use these cheats, right? So we first choose ourselves a signature and then program the random oracle such that the message actually hashes to a corresponding hash value, which for which the signature verifies. And of course, we store mj comma sigma j, the corresponding signature, and the hash value hj. Right, and of course, as an output, he doesn't get hj, but just the sigma j. Now, of course, he also can do hash queries to the random oracle. So this is the sign oracle. Here's the hash oracle. The hash oracle, he asks these mi prime. And we're going to do the following. If I is not I star, in I star, we want to embed our own challenge C. Then for every new, new mi, we again choose a sigma prime in Zn uniformly random, and sorry, and we set hi prime to be sigma. What did I call this? J? No, this is sigma I. This is not J. Sigma, this is an I, hi prime is just sigma I prime, there's also a prime here, to the E mod n. And of course, we store this mi prime, comma, sigma I prime, comma, hi prime. But here's the thing, if I equals I star, we just set hi prime to this C, right? Where this C is, of course, taken from here. Okay. In the end, we just have to finish this adversary. In the end, he gives us this m star comma sigma star, and we just check if sigma star to the E mod n equals C, output sigma star. Good. This is our RSA adversary A prime. We kind of have 3 minutes remaining. Let's quickly reason why this adversary works. So the first thing is that we've seen we can compute signing queries by just choosing the signature before the hash value, right? So what was actually a flaw in the textbook RSA signature scheme, we've turned into a virtue here, that we can choose signatures before using the message. Because if we choose the signature uniformly at random, then the message is also chosen uniform, or this sigma sigma j to the E is also distributed uniformly random, and we can pretend that this hj is actually a valid output of the random oracle. Oh, sorry, one thing is missing here. What goes back here are sigma I prime, the same as the same for when we simulate the random oracle. So what we actually do is we're not just choosing a random value h, but we're choosing it directly together with a pre-image sigma prime, such that if an m that he got from here is later queried to the let's say signing query, we already know the correct signature for it, right? We already have this tuple m prime, mi prime, sigma I prime, and hi prime. So that's the idea. Instead of again, simulating these two oracles independently, we simulate them jointly. But my time is over. I'm gonna leave this here for now. I'm gonna leave this sketch, and we'll meet again one last time on Thursday. All right, thanks everyone. I'm gonna stop the recording now.